All right, good morning. Welcome to week 7. Good morning. So, what I want to do today is go over Lab 5. So, Lab 5 is graded and returned with some comments and such. So, I want to go over Lab 5. I want to talk about timing diagrams. I want to talk about the circuit for Lab 5 because it had some peculiarities. And along those lines, I want to kind of talk a little bit about labs in general and why we do labs in this course and different approaches to doing lab and why they may be important in different ways from how you might think. So I want to talk about labs in general. We're going to do more state machine analysis, and then we're going to move on to Lab 6, which you'll have 2 weeks to do, and that'll be your last traffic light lab. And then we'll move on to state machine synthesis, which is the end of the state machine part of the course. So that's sort of my plan for the next 2 classes, so today and Wednesday. And then I also want to go over the midterm and just sort of make some comments on that. Midterms look pretty good overall. So just a few comments to make on that. So let's begin. If there are any questions anybody wants to ask up front, this would be a great time to do that. All right then. Well, let's go ahead and start with the midterm then, and get that out of the way. So first page, not a lot of problems for people, other than maybe careless mistakes. And careless mistakes will cost points. They won't cost you, all the points if you show your work. And I can see that there was a method that got you to the answer, and there was a mistake in that method. That'll cost you some points. If there's no work and the answer is wrong, then you lose all points. So how do you convert the number 266 into these other formats? Well, once you get it in binary, it's easy to go to hex and octal because you just group the digits together. But how do you get 266 into binary? Well, if you've done a lot of binary, you remember that 256 is 2 to the 8th. And so this is 256 plus 10. And you could write down 256, 128, 64, 32, 16, 8, 4, 2, 1. And chunk it out like that. But if you don't happen to know that 2 to the 8th is 256, you can use this technique that we went over in class. 266 divided by 2 is 133 with a remainder of 0. 133 divided by 2 is going to be, whatever it is, 66 with a remainder of 1. Tell me if I make a mistake. 66 divided by 2 is 33 with a remainder of 0. 33 divided by 2 is 16 with a remainder of 1. And then 16 divided by 2 is 8 with a remainder of 0. And you gotta be careful at the end. So 4 divided by 2 is 2 with a remainder of 0. 2 divided by 2 is 1 with a remainder of 0. And this is the last one where you get the most significant bit. You take that 1. 1 divided by 2 is 0 with a remainder of 1. And then those zeros divided by 2 will just be 0, remainder 0. And those will repeat forever. So most significant bit is sitting right here. 1 and then 4 zeros. and then a 1 0 1 0. So if I break it into groups, it looks like this. So what is your correct answer? Right, that's what it is in binary, and you can put the subscript 2 if you want, or if you're answering the question what is it in binary, you just need the number part. And then how do we write that in hex? Write a hex digit for each group of 4, so we can always pad zeros into the beginning without changing the value. So this becomes a 1, this becomes a 0, this becomes the letter A. And then in octal, break it into groups of 3. And so there's a 4, right, 1 0 0, there's a 0 0 1 is 1, and there's a 0 1 0 is 2, so it's 412 in octal. All right, the next one, there may have been a conceptual issue here as to how 2's complement works and what it is. So if I ask you to write the number 5 as an 8-bit 2's complement number, right, it's just your usual weighted positional notation. That's positive 5. If I ask you to write negative 5, it means write positive 5, toggle all the bits, add 1, that's negative 5. If I ask you to write the negative of this number, toggle all the bits, add 1, this is the negative of that. Well, this is negative 5, which is, guess what, positive 5. So 2's complement is a methodology. It's a protocol we use to express a number in binary that allows us to express both positive and negative numbers. Weighted positional notation only lets us express non-negative numbers, and we find the number by adding powers of 2. But 2's complement lets us write positive and negative numbers in binary. And the procedure is simply, if you have a positive number, which you know because this most significant bit is a 0, and you want to change it to a negative, toggle all the bits, add 1. And if you have a number which is negative, which you know because this first bit is a 1, and you want to find what its value is, well, you can take the complement of all the bits, add 1. That will give you a representation for negative this. Well, since this is equal to positive 5, that tells me this was negative 5. So there were some people on this question that began by writing negative 76 in binary somehow, and then toggled all the bits and added 1. And so the answer they put down was the expression for positive 76. So writing something in 2's complement does not mean toggle all the bits, add 1. Right? It means if the number is positive, write the number with weighted positional notation. If the number is negative, take its absolute value, write that in weighted positional notation, and then add 1 to the complement of each bit. What would happen if there is a 1 that is carried past the most significant bit? It flips back over into a positive number, but I don't think that can, well, maybe that can happen. But you always, if you're doing 8-bit 2's complement, you just look at the low 8 bits. And if there's a carry out of here, don't worry about it. But if we have something like, 0, and you want to find the expression in 2's complement for the negative of this, well, toggle all the bits and add 1, and you're going to ripple that final carry all the way over. That's how you represent negative 0, which in a reasonable world should look the same as positive 0. So that's one number that's both positive and negative. All right, so again, the key point here I wanted to make, if someone says to write this number in 2's complement notation, it doesn't mean write this number and then toggle all the bits and add 1. right? It means if this is positive, just write it in weighted positional notation. If it's negative, write the positive value in weighted positional notation, toggle all the bits, add 1. So you could do this by saying positive 76 equals, and if we could do this, but I know 76 is 64 plus 12. So I'm just gonna kind of do this in my head. 128, 64, 32, 16, 8, 4, 2, 1. So that's 4 and 8 is 12, and 64 is 76. So if I want negative 76, I'm going to toggle all the bits. I'm going to add 1. There's your representation for negative 76. Now there's a trick you can do for 2's complement, which is, you know, if you want to toggle all of these bits and add 1, start from the right. And if you have a 0, keep that 0 and move over. If you have a 0, keep that 0 and move over. If you have a 1, keep that 1. But now, for the rest of the number, just toggle the bits. And that's a shorthand way of saying complement all the bits and add 1. If you have zeros, starting from the right, keep them until you get to a 1. Keep that first 1 and then toggle everything else. But it's only a slight time saver over, you know, actually toggling the bits and adding 1. And I saw, I think, 2 people who tried to do this, I think, on the question and got the answer wrong. But it's very hard to show work if you're just going, you know, from here directly to there in your head. And so if you do this, you know, and you forget to carry a 1 or something, I know, okay, they know how to do a 2's complement. But if you're, you know, on the job and you've got 1,000 numbers you need to convert to 2's complement before lunchtime, right? This is a handy trick, but hard to get partial credit. All right, and then writing the decimal number here. So most people were fine with this. Break it into 2 pieces. So the number 2 is just 1 0. And then you can multiply by 2 and subtract 1 repeatedly. Or you can do this in your head. And so your negative powers of 2 are 0.5, 0.25, 0.125, 0.06, 25, 0.03125, and so on. And so this one and that one get you what you're after. So it's 0.101. All right, so that was playing with conversions. Circuit diagrams. So design a circuit with 3 switches, and the LED should light when exactly one of the 3 switches are open, meaning a logic 1. Remember, when we open our switches, that pull-up resistor drives the input to 5 volts. So open means 1 in this course and in 270. So I asked you for specific pieces, right? System diagram. So system diagram, the main purpose here is to name our inputs and outputs. So I might call my inputs A, B, C, and maybe I'll call my output L. And I could say, you know, L equals 1 when exactly one of A, B, C equals 1. So that's a complete description of what the circuit does. And then a truth table. So here's the real heart of the matter. Thank you. So L should be 1 when exactly one of your inputs is 1. So that's here, here, and here. And then it's going to be 0 everywhere else. And then an unsimplified sum of products. So L equals, and just write down your equations where your output is equal to 1. So A bar, B bar, C, or A bar, B, C bar, or A, B bar, C bar. And I didn't mean this to be tricky, but I asked you to simplify the SOP, and you can't simplify this using a K-map. That might have seemed confusing. That was unintentional. I thought the K-map would make it simpler. It turns out if you do a K-map, it does not change your equation. But that's okay. That happens sometimes. So we want ones in 0, 0, 1 and 0, 1, 0 and 1, 0, 0. And there's no better covering than just that, which means that your simplified equation will be exactly the same. So if we had a 1 right here, that would be an XOR. But if we look at 1, 1, 1, right, 1 XORed with 1 is equal to 0. And then if we XOR that with a 1, we would end up with a 1. So an XOR of all three would give us a 1 out here also. So it's slightly different. I only took off a couple of points if you used an XOR because it could have felt like a trick that I wanted you to simplify it, that you're supposed to go to an XOR, and that was not my intent. So I only took off a few points for that. All right, so this is also your simplified equation. And then to sketch the circuit, well, you can do your usual business. And this is potentially, not very pretty, but it doesn't have to be pretty, right? You want to get it done. And I said, don't worry about pin numbers and part numbers, but show logic gates, switches, and LEDs. So so we need A bar, B, C. We need longer wires. A, B bar, C. A bar, yeah, I should have done this on a separate page. A bar, B bar, C, right? So we could have A bar, I'll stick to my equation that I wrote. A bar, B bar, C, A bar, B, C bar, or A, B bar, C bar. And then those have to go into an OR gate. And there's your output. So your switches, these need to get pulled up to 5 volts. And then you use a switch to connect these to ground. So there's C. Here's B, and here's A. Right. So the setup is these lines are normally connected to 5 volts through a resistor, so they're logic 1. But if you close this switch, then this point gets connected to ground, this gets connected to ground, and so on. And so the behavior is when the switch is open, you get a logic 1, right? This is the open position, those inputs go up to logic 1. And then on the output side, you just need a resistor, an LED, and then connect the output to ground. So now when the output is a 1, the LED will be on. All right. Write an unsimplified product of sums in canonical standard non-compact form. So standard form is this. This is the non-compact form. For sum of products, the compact form is something like this: sum of 1, 2, 4. Right? That's compact. This is non-compact, which we said is also called canonical. So here we want to write product of sums in canonical form, and then write it in compact form. So product of sums, look for the rows where your output should be a 0. For product of sums, we're going to write a product of sums. So we're going to have, sum, ANDed with something else, ANDed with something else, ANDed with something else. And the sum term comes from, A, B, and C. And the rule for POS is if we have a 0 in the input, we write the variable without a bar. So it's A or B or C. And this row is A or B bar or C. This row is A or B bar or C bar. And this row we have bars over everything. So that's the non-compact form. And then the compact form, f of A, B, C equals, well, it's a product. And which rows do we have a 0 in? So it's rows 0, 2, 3, and 7. And some people simplified this and used that for the compact form. Compact form is not the same as a simplified expression, right? Simplifying, we put it in the K-map, and we find ways to write smaller sum terms in this case, right? By grouping things that are in common and so on and so forth. Compact form is writing this in terms of max terms in this case, right? And when you do a compact form, make sure you know what the order of the variables are by saying, f of A, B, C, for example, so that we know that this is A is a 0, B is a 1, C is a 0. A is a 0, B and C are both 1s, and so on. So that's compact. But then in question 4, you get to use a K-map. So here we're trying to find a sum of products. And on this one, a few people had some troubles with the K-map itself. And the main trouble there is how you number these. And this if you flip these around, you get a different result. So make sure you do this gray code ordering. So 0, 0, 0, 1, 1, 1, 1, 0. And then I recommend just filling in the 1s, not the 0s, because it makes it easier to visually see what's going on. So I'm just going to write in the 1s. So 0, 1, 1, 0. 0, 1, 0, 1, 0, 1, 0, 1. 0 dash dash 0. And then 0, 1, 0, 0. So there's your ones and don't cares. And then how do we cover that? So that's a good cover for those two. The don't cares, we're allowed to cover those if they help us, and they help us a lot here because we get a 4x1 cover. And 4x1 is going to be better than, a 2x1 and a 2x1. And then the sneaky one over here, we can wrap around the edges so we can actually do a 2x1 for those as well. And then you write the product term for each of these expressions. So this rectangle right here, A is a 0, so that's A bar, B is a 1, C is a 0 or 1, so it doesn't matter, and D is a 1. And then this long skinny one, A and B can change between 0 and 1, so A or B don't matter, but C is a 0 and D is a 1. And then this this broken rectangle. John Travolta movie. A can be a 0 or 1, so it doesn't matter. B is a 0. C is a 1. D is a 0. So your simplified expression would be F equals A bar B D, or C bar D, or B bar C D bar. Alright, true, false. Any logic circuit can be built from a combination of XOR gates. That is false. XORs are not universal. You can't build an AND gate out of an XOR. I spent like a month trying when I was an undergrad. Does not work, right? So this is false. But an XOR gate can be constructed from NOR gates. That is true. You can construct any logic gate from just NOR gates, because NOR gates are universal. And we saw, you know, a schematic of the Apollo guidance computer built entirely from NOR gates. So that's definitely true. An unsimplified POS sometimes has fewer terms than the corresponding unsimplified SOP. That is absolutely true. Either one could be simpler. In particular, if you had a truth table with ones everywhere except for one term, and it was a 4-input truth table, right, the unsimplified SOP would have 15 product terms being added together. The unsimplified POS would be a single OR expression, a single sum. One can connect 2 full adders to make a 2-bit adder. That is absolutely true. That's how we started working with our half adder full adder design. First we connected 2 full adders, and we connected the first incoming carry to ground, and then we said, hey, since we're not using the carry, let's just eliminate that part of the circuitry in a full adder. And that's what became the half adder. So that's the simplified version of a full adder, where the carry in is always 0. But if you only have full adders, you can make a 2-bit adder out of that. Just ground out that first carry coming in. And then 2's complement is the only way to represent negative numbers. That's certainly false. We have signed magnitude notation, where you just put, you know, a 1 in the most significant bit to say negative. That's what we do when we write decimal numbers. If I want to write the number 76 as negative, I just throw an extra symbol in front. Well, that's what we called signed magnitude. Here's the magnitude of my number. Here's whether it's positive or negative. And you could simply, you know, come up with your own coding of numbers, where, you know, these numbers represent these values, and some are positive, some are negative. There's nothing unique about 2's complement, right? Except that it works really well for doing arithmetic. All right, and then finally the fuse map question, which I thought was a give me, because everybody, you know, pretty much everybody got full points on the homework questions about fuse maps, which were more complex than this, I think. Label all the inputs and outputs. Well, we have 4 inputs, A, B, C, D, so I'll just label those right here. And we're going to have 3 outputs, F0, F1, F2. And so we've got a programmable AND plane and OR plane. Now you can draw these with dots or X's, I don't care. I'll go ahead and do X's, just because it's more fun right now. So F0 is going to be a sum of 3 terms, AB. So I'll go ahead and mark off AB, and that's this line right here. BC, so I'll mark off BC, and that comes out of this AND gate. And AC, so I'll mark off AC, and that comes out of this gate. So that's F0. F1, we want A ANDed with B bar. I'll skip a line just for fun. So here's A and B bar. And then CD is going to be C and D. So there's F1. And then F2, I can reuse terms, right? So F2 should be AB. Well, I'm already calculating AB with this AND gate, so I can just feed that into F2's OR. And I'm already calculating CD down here with this AND gate, so I can feed that into F2's OR. And so there's a good fuse map for for generating those functions. And if you didn't share these terms, if you recreated, you know, A, B, and C, D, that's fine. You got plenty of space on here. But you only needed 5 rows from here. So any questions on the midterm? So deductions, switch issues on the schematic, some issues converting the pieces of a K-map, these covers, into expressions, which is just an algorithm, right? See which inputs are changing inside here. The ones that change don't matter. The ones that don't change, for sum of products, if the value is an A, we write the variable without a bar on top. If the variable is a 0, we write that variable with a bar on top. A few people who tried to use XORs, which we already talked about. All right, so any questions? Homework 5, question 5. What's the answer to that question? Anybody remember? Anybody remember question 5, homework 5? Timing for a circuit? Yes, I said to skip it. So, because we didn't go through that last week, so I said don't do question 5 on homework 5. We'll do it in a future assignment. So that's the easiest possible answer. But we are going to go through that this week. That's okay. We'll go through that because that's an important concept, right? That's how we figure out how fast machines can run. But I didn't want to rush through it last week, and at the time I thought the homework was due Monday. It's actually due Wednesday, so we could have gone through it, but I'll just put it on homework 6 instead. And it comes down to a question of thinking about hold time and setup time on flip-flops and propagation delays on combinational logic. All right, let's talk about Lab 5. So Lab 5 was kind of mixed results across the class. So some people nailed it, which doesn't necessarily mean that they got all their circuits to work. There was this glitch in Tinkercad when you try to reset the counter. But the lab report is not, saying that you got all of the results that you were hoping to get, right? It's a lab. It's an experiment. And I was thinking about this earlier. I just wanted to kind of talk a little bit about why we do labs at all, right? Why do we bother with these? So when I was an undergrad, right, I hated lab work. because I was used to just sort of like plowing through homework as quickly as I could, and then I'd like go on to like the other things I really wanted to do. And labs I could not plow through quickly because you had all these steps you had to follow and all these things you had to write and so on. So I tried to treat them like homework questions and work through them as quickly as possible. And if there was something I could do without actually doing it in the lab, I would try to get away with that. And it worked, I passed my courses and so on. But I missed out on something really valuable that I ended up, learning later on instead, which is this idea that, as engineers, you're problem solvers, right? That's why people will pay you to be an engineer, is because you can solve problems. And it's not going to be problems like x plus 5 equals 20, find the value of x. Well, that is a problem that you can solve, but we have machines that can do this. This is not why someone will hire you as an engineer, right? People will hire you as an engineer because their system is broken and they don't know why it's broken, right? And it's not like homework question 17 back in that course you took 2 years ago. Something's wrong with the system. It should work, but it doesn't. Maybe there's a loose wire somewhere. And so how do you solve problems in the field, right? So typical problem, right? Somebody's got a business, they've got their web server running, and every morning between 7 and 9 the server keeps crashing, right? And it's your job to fix that. Well, that's not a homework question, that's a lab question. Right? So why is the server crashing from 7 to 9? Well, I think that's when people wake up, and while they're having breakfast, they're hopping on the server to check their portfolio or whatever, right? So how do you test that hypothesis? Well, maybe you create a different website that people will connect to that records their access and then forwards them to the real site. And now you're gathering data. And you can run this for a few days, and you can take all this data, and now you've got information about how many people tried to access this website when. And maybe you also record how many times the website crashes. And now you've got 2 sets of data. Well, maybe you're going to, tally those up in some way. Maybe you'll take a running average or something, and then you'll graph them side by side with each other, something like a timing diagram, right? Here's the volume of requests to the website, and here's how many times it crashes, and all of a sudden it jumps up, right? And it jumps up when the volume of requests exceeds this one threshold. And now, you've got some data to back up your hypothesis. And so you refine your hypothesis, and you do some more experiments, and eventually you figure out what the problem is, right? So that's sort of the core of engineering. It's this problem-solving thing. And labs are really kind of an exercise in that. It's exercising those muscles that we use to develop hypotheses, come up with experiments, run experiments, collect data, analyze data, draw conclusions. And then, if we're, doing science on a large scale, publishing those results, right? So writing them up in a way that lets other people see what we did. If you're trying to fix your company's server, you're probably not publishing the results, though, right? You're probably keeping it as your secret for your company on how to handle high network traffic. But for us, we're writing up our results to share theoretically with others. So Lab 5 was a funny little pair of experiments, right? So the first part of it was playing with this different chip, this 555. Have a good day. See you later. And the 555, it's an analog chip. It's different from, AND gates, OR gates, these things that are generally well behaved, right? This is an analog device. It has resistors and capacitors and things like that connected to it. So it's a different kind of bird. And you can use this in a lot of different configurations, and you can do a lot of different things with this. You can have it generate pulses. You can have it generate nothing but receive pulses. And if a pulse is missing from a regular pattern of inputs, then it will fire an output. And you can use it as a missing pulse detector. You can use it as a one-shot, where when some event occurs, it will generate an output pulse for 2.5 seconds and then drop back to 0. There's a lot of configurations. So this is called the astable configuration, where it's just generating a pair of outputs, high and low. And in this configuration where you wire it like this, right, these equations tell you how long the circuit is high and how long it's low. So meg is 10 to the 6th, micro is 10 to the minus 6th. So this is basically 2 million times 1 millionth. So this expression here turns out to be 2. This expression turns out to be 1. So the short version of that is the time high is approximately 1.4. Time low is approximately 0.7. So I wouldn't approximate those in your lab. I would actually, plug in 0.693 times 2 for the high and for the low. But that's ballpark, what the output should look like. And so if you wanted to draw a theoretical version of this, I could put seconds down here. Now if it's high for 1.4 and it's low for 0.7, the total period is about 2.1 seconds. So just about 2 seconds. And the output, which is pin 3, well, it should be high for almost 1.5 seconds, and then it should go low. And then it should go high again for almost 1.5 seconds, and then it should go low. And then it should go high again, and so on. And you don't have to draw a million of these cycles, but you'd like to see at least a transition from high to low to high to low. Right? And again, if I only show you this much, it doesn't tell me how long the signal is high, because I don't know how far this went in this direction before it went high. I don't know how long this continues in this direction before it drops. But if I show at least that much, and I believe this signal is periodic, then I can clearly see the low portion and the high portion. So you can draw a few more of these, if you like, and then you can just annotate them and say time high equals 1.4 seconds, and down here you could say time low equals 0.7 seconds. And this is theoretical. All right, and then on the observations, I didn't want to create a new circuit. So here's just the 555 portion, right? So I've got my 555 capacitor, and so on and so forth. Capacitor is 1 microfarad. The resistors are mega ohms. And if you set this thing up to 1 millisecond, and you run this, well, you get this as your observed waveform. And again, that's not incredibly useful. All I can tell from this is that at some point the signal changes from 0 volts to 5 volts. But timing-wise, that's not very satisfying, right? I mean, this waveform also describes the light in my living room, right, which is off overnight, and then in the morning it gets turned on. But that's not very informative. So you can change the settings on this. So if I change this to a microsecond, right? Well, this is a shorter time period from here to here, but it's still not really giving me any information. So if I make this time per division bigger, like if I make this a second, and you have to kind of wait for this to kind of do its thing. Now I start to see something like a waveform. And there's something weird going on over here. This should be a periodic waveform. It should always do the same thing, however high and low it is. So let's try this with, instead of a second, let's do half a second. So let's do 500 milliseconds. And give it a second to stabilize. And now we got, you know, something pretty close to what we were drawing here. Right? So I might zoom in on this. And, you know, we've got these marks down here. This says this is 5 seconds from here to here. And there's a total of 10 of these lines, so each of these lines is half a second. So a pair of lines gives me 1 second. And then 20 volts going from the top to the bottom, and there's 10 divisions from top to bottom, so each of these lines is 2 volts. So there's 2, there's 4, up here is halfway through the next division, that's 5 volts. So now I can screenshot this, and I can draw that, and say, you know, this was the observed waveform. And as we said last week, you know, if we do this with an actual oscilloscope, it won't be these nice square corners and so on. It'll have some slop and some noise and some ringing and so on, and it makes it more interesting. But we can certainly draw this, you know, from this we can look at this oscilloscope trace and say, you know, here's a theoretical waveform, and yeah, it basically looked like what I expected, right? So that's you know, half one, a little less than 1.5 seconds high, and a little less than 1 second low. All right, so that's experiment 1, and that's critical because you're going to use this 555 for experiment 2 here, and you're going to use it in lab 6 for your traffic light control. And so experiment 2, we're doing the synchronous up counter. So the 7493, we're going to count from 0. We're supposed to count up to 9 and then back to 0. All right, so system diagram we talked about is kind of goofy in this one because there aren't really any inputs, and the output is either, you know, the visual display, or maybe 7 outputs to the 7 segments, or 4 outputs from the 7493. It depends how you want to draw it up. So some kind of system diagram, right, with a description of what the outputs do. Detailed schematic, timing diagram, and test plan. All right, so this one had some challenges, and so let's go back to our circuit. So this was the first version I tried. I built up to this. First I used a function generator instead of a 555 because I don't like wiring 555s. But we can run this, and the output of the counter I'm using to drive a set of LEDs instead of a 7-segment display. And my reset circuit, which should reset when I get to 10, is coming out down here. So there's counting to 7. Here's 8, here's 9, and then instead of 10 it goes back to 0. And we couldn't see it, but this LED flashed very briefly, and that was the reset signal. And you know, here's the output of the 555, so I've got that going on in LED, so I can look at it and see, yeah, things are blinking, that's great, the 555 is doing its thing. And if I want, right, if it's not resetting, I can do what? I can take this wire and I can just move it somewhere bogus. Alright, so these are tricky to move, but I think the trick is if you can highlight the wire itself, then you can grab an end. Oh, thank you. you can grab an end and drop it somewhere else. And then I'm going to go ahead and I'm just going to connect this reset line to power. And so if I run this, when my output is 1010, I broke something. Oh. Sorry, I need to connect the reset to ground. So when the output is 1010, right, I'm taking those two ones, running them through an AND gate, taking those two zeros, inverting them, ANDing those with the two ones. That's what I'm using to generate this reset signal. And we're up to 7. When this gets to 10, this reset line should go high. So there's 8, there's 9, and there's 10, and there's the reset signal. So it's not going anywhere right now. But if we connect that reset signal to the reset input on the counter, then when we get to 10, the circuit resets. And you know, our capacitor is 1 microfarad. If we made our capacitor smaller, so if we go to nanofarads and instead of 1,000 we make this, you know, 200 nanofarads, this will count 5 times as fast. And so if you're tired of spending 20 seconds every time you want to test your reset circuit, you can speed it up like this. All right, so that's you know, testing the reset circuit. And what's the reset circuitry look like? Basically, if I want, you know, data 0, 1, 2, 3. I want my output to be 1 when my input is 1010. So count 7, 8, 9. When it gets to a 10, set a reset equal to 1, and I want it to be 0 everywhere else. So as a sum of products, I have a single row with a 1 output. And so my equation is going to be reset equals D3, D2 bar, D1, D0 bar. So if I have my circuit generating, you know, the output of my counter like this, I'm going to take D0 and D2, run those through a pair of inverters, and those together. And I'm going to take D1 and D3 and those together, and then AND those. That's my reset circuit. So these are 7404s. These all come from a 7408. Which is what this setup is doing down here. So then there's the issue of, okay, so let's do the 7-segment display, and that's where things get wonky. And so what a lot of people discovered is that when they take their circuit and they try to run the output through a 4511, right, which is right here, and then go into a 7-segment display, you get unexpected behaviors. So here I've disabled my reset circuit and I've disabled the display, but when I get to the point where the counter should roll over, my simulation time almost freezes. It slows down considerably, right? This should be real time, and it's doing so much calculation it can't keep up with real time, and so we're seeing a millisecond pass every 2 or 3 or 4 seconds of wall time. And this is a problem in the simulator. And I've got most of my outputs from my counter not going anywhere. Right, I have one output connected to the 4511, and that's enough to induce this kind of behavior. I've also disabled the reset circuit, although it doesn't look like it's disabled. But anyway, so it's not the reset circuitry, it's not the counter itself. It seems to be something over here. Now some people replaced the 555 with a push button and were able to get this circuit to behave properly with a push button. And almost certainly this is some kind of timing issue inside the simulation. And some of the exercises in the book with flip-flops, you find that there's situations where if you violate setup and hold times, if you change an input right before or right after a clock tick, those cross-coupled inverting gates can end up chasing oscillating patterns of ones and zeros. And I think that's what's going on in here. Well, whatever the cause, the behavior is that when you try to simulate your circuit, right, the simulation does not proceed beyond a certain point. It seems to get hung up. And, you know, 9.467 is right around the time where the reset circuit should be kicking in. In this case, I had a sped up capacitor. So, you know, there's information in there, right? You can observe the time where this happens and describe what should be going on in your circuit. And you can take your circuit apart. If I disconnect this one wire from this 4511's input, then the system will reset correctly. When it gets up to 15, it'll go back to 0 and so on. So I can take this and just move that wire somewhere out of the way and run my simulation. And so there's 1, 2, 3, 4. There's 8. Our simulation time is continuing to increase and it's matching wall time. There's 14, there's 15. And it saw a little bit of a thing pop up there when it tried to do the rollover, but it rolled back over to 0 and it continued. So here's 15, and then it goes back and it continues again. So there's lots of stuff going on in here. It's not the thing that we necessarily expected, but there's lots that you can observe, and there are other experiments you can do, and there's things that you can write up. And this is a really interesting experiment if you were actually doing this to like publish your results, because it's unexpected, right? Everything that you know says that this should, you know, act a certain way, but it acts some way different. That's the fruit fly with, you know, one red eye and one blue eye. And you don't just discard that sample and say, there must just be an anomaly, you know. That's the one that like moves science forward, right? This is the thing that like changes the world, you know, 100 years from now. So these are, you know, good things. All right, so I told people, you know, for this, if your circuit's doing this, just go ahead and, you know, record what you observed and move forward with that. So that's perfectly fine. And so that was experiment 2, right? Oh, timing diagram. So when we talked about this, I said for the timing diagram, at the least, you want to include the 555 output, the 4 bits of output from the counter, and ideally your reset output. Now, some people discovered or thought up that, you know, there's 2 reset inputs here on the counter, and if both of those are 1, then the counter will reset. And so some people, instead of building this circuit, said, oh, let's just take D1 and connect that to the one reset input, and take D3, connect that to the other reset input. That works great, does the same thing as this. Because the first time both of these bits will be 1 is when you've counted up to 10. And at that point, those 2 bits reset the circuit. So that's awesome. It would be really nice if you talk about that in your write-up, so that someone looking at your circuit says, wait, why is D3 going back into the counter, right? It's a cool way to do the reset. So just, you know, describe that in the write-up or in the schematic, right? And that's a good reset circuit. All right, so what does the timing diagram look like? So time runs horizontally. Yeah, I'm going to need more. This works great on graph paper, by the way, but, you know, in a pinch. So first thing we want is the 555 output, because that's what's sort of driving everything. And you know, we know the 555 is asymmetric. It's high for a little longer than it's low, but I'm not too worried about that. So I'm just going to kind of fake this. And with a timing diagram, your goal is to show the behavior of the circuit. Well, this circuit, we know, takes at least 10 seconds to do all the things that it can do. It can count 0, it can count 1, it can count 2, it can count 7, it can count 9, it can reset back to a 0. So you want at least, you know, 10 cycles of your system clock to be able to show all of that behavior. And you probably want at least 11 because, you know, we always want to see, like, you know, something moving from low to high back to low, or vice versa, high to low to high, so we can see what's happening on either end. But, you know, show a bunch of cycles. And I don't know which one we're going to call least significant bit, but I'm just going to call this D0 as our least significant bit. And if you go back to your simulation, right, you can do this theoretically, or you can do this experimentally. Ideally, both, maybe. So let's change our capacitor, and instead of 300 nanofarads, let's go back to 2 microfarads. So this will be a nice slow simulation. So my timer output is high. And maybe I didn't want it that long. Maybe it's too slow. Should not try to do metric in my head. Oh, I made it 20,000. Okay, let's do 2,000. Well, let's just do 2 microfarads. So this should be about a 4-second period. So our timer output is high. And then when it drops low, this bit changes to a 1. Timer goes high. When it drops low, this bit changes to a 0. Timer output is high. When it drops low, this bit changes to a 0. So I'm looking at the timer output, and I'm looking at this least significant bit, which I'm calling D0. And it changes when the timer drops from a 1 to a 0. So this is negative edge triggered. Right? Normally we think of, you know, when a clock ticks, it's going from 0 to 1. Well, in this case, the tick is actually when it drops from 1 to a 0. And that goes along with the data sheet. If you pull up the component spec on this thing, and you look at this picture of what's going on inside, right, here's your clock input. It's input A. It's going into the clock of a JK flip-flop, but there's that little circle on the outside. That means it's a negative edge-triggered device. So this is going to count on the falling edge of the clock signal. So experimentally or theoretically, right, you can describe what this should be doing, which is if the output starts low, every time the clock drops from 1 to a 0, this should toggle. So it'll toggle like that. All right, and if you go back to your simulation, you look at this least significant bit. When that bit drops from a 1 to a 0, the bit next to it toggles, right? This bit is on. The next time this bit drops from a 1 to a 0, the bit next to it will change from a 1 to a 0 also. So this bit D1 toggles when D0 changes from a 1 to a 0. And that also goes along with the data sheet describing the chip, because we take the output D0, you feed that into input B, which is a negative edge-triggered input on that next JK flip-flop. And if you write out the numbers from 0 through 9 in binary, you observe this pattern that every time this bit changes from a 1 to a 0, the next bit toggles. This bit changes from 1 to a 0, the next bit toggles. And when this bit changes from a 1 to a 0, the bit next to it toggles, and so on. That's one way to write these input combinations in truth tables, is to just keep toggling bits, and every time this bit drops from 1 to a 0, toggle the bit next to it. So since D1 is doing this based on D0, every time D0 drops from a 1 to a 0, D1 should toggle. And D2 is the same way. Every time that D1 drops from a 1 to a 0, D2 should toggle. And D3 toggles every time that D2 drops from a 1 to a 0. But then we also have this reset signal. And reset is low until our input combination is 1, 0, 1, 0. And at this point right here, so D0 is a 0, D1 is a 1, D2 is a 0, D3 is a 1. At this point, your reset goes high. And at that point, something different happens. And so I might mark this and say count equals 1, 0, 1, 0. And at that point the reset line goes high. And when the reset goes high, this is going to go back to a 0. D2 is already a 0, D3 is going to go down to a 0, and once these counts go down to 0, then the reset line will go back to a 0 also. And now I have to redo these parts of my timing diagram, so every time that D0 drops, D1 should toggle. And D1 will not drop in this example, and D2 will not drop. So there's what my timing diagram looks like. And I could, put a little annotation here saying reset pulse clears count. And that's what your circuit should be doing. Now in Tinkercad we get up to this point and then something freezes and we don't know what it will do after that. But I let it run for a couple of hours at home, and it never got past this part of the timing. Alright, if you didn't show the reset pulse, I didn't take off points. But if you didn't at least show the 4 count outputs, then there was a deduction there. And this is a synopsis of all of this. Right, big circuit, lots of parts and pieces. So I could have squeezed it onto fewer boards, but to keep things where you can follow what's going on, I spread this into 4 proto boards. It's a pretty complex circuit, right? But this is a pretty succinct representation of what the circuit is supposed to do, what its behavior should be. We can't describe this with a truth table, because we don't even have an input, right? So truth table doesn't make sense. It's got to be a timing diagram. But this shows you, D0 is changing not as quickly as the 555, but half as quickly. D1 is changing half as quickly as D0. D2 is changing more slowly. The reset pulse comes up every 10 clock ticks, and so on and so forth. All right. So the other comment on Tinkercad, I'm going to require that when you do circuits on Tinkercad for Lab 6, that you treat these like physical protoboards, which means maximum of 1 wire per hole, right? So if I wanted to do something with this signal right here, right? I can put this signal into this hole up here. I can pull it off of the LED in this hole. I can feed it into my decoder in this hole, and I can run it into my reset circuit from this hole, right? Instead of shoving all 4 wires into one hole. So 1 wire per hole. Make sure all your parts are sitting on the board, right? Tinkercad, I can actually have this chip just hanging off on the side here, and I can still connect to it, but make sure they're actually on the board. Don't run wires underneath chips, because you can't do that on a physical board. Run them around. And try to make your Tinkercad layout look like if you were to build this on a physical circuit, something you would be happy trying to debug, right? So it takes a little more time, but Tinkercad is pretty friendly about this, right? I can grab a corner and move it around.
I have a question.
Yeah.
Do you want us to try and create it as one continuous board, or do you want us to have it like yours, which is just segments?
Totally up to you. Whatever's going to make it easiest to wire. So Lab 6 in particular, people usually use 2 or 3 of the long protoboards when they actually do this in the lab, because you have to rebuild your traffic light circuit from an earlier lab, and then you have to add extra circuitry to it, and that extra circuitry usually breaks out into like 3 or 4 pieces. But you can do it however you like, whatever's going to help you organize it logically, so that you can successfully build it. I usually prefer to work on just a few big boards, but I knew there was a problem here, so first I just built the counter and I drove it with a function generator, and then I put the 555 on a separate board, and then I added the reset circuit, and so it just kind of logically broke out this way for me. And a few things that I sort of stumbled across playing with this. So like if I wanted to connect this bus to that bus, right? I can do this, right? And that's okay, but it's a little confusing perhaps if I have lots of wires just kind of crossing over each other. So I mean, you can double click a wire and add an anchor point like that, and I could add another one. And when you get these wires horizontal or vertical, you'll get a little guideline that tells you that. And so I could grab this one and I could move it around till it's got those. And now I've got something that's pretty easy to see. Hey, it goes from here over to there. It's not connected to other things along the way and so on. And color coding is fun, right? Anytime you can play with color, it's a good day. So you can take advantage of that. But I'm not going to get dogmatic about what your Tinkercad circuits look like. But for your own peace of mind when you're trying to debug the circuit in Lab 6, right? If you do something where you can look at it and easily sort of like see where your wires go, it's going to make life easier for you, right? So think about that. And I've got a feeling if you end up doing 270 with Izod and you have 5 wires stuffed into one hole, you might lose some points. I think I might take off points in 270 also. I don't know. So something to keep in mind there. All right, and then the usual stuff. So cover sheet fine, lessons learned, lots of good new experiments. I like the new experiments, so keep those going. And all of that stuff was good. Typical length for these lab reports I'm getting 20 to 30 pages, right? Which is not unreasonable if you're including lots of screenshots from Tinkercad. You're developing your circuit and showing how it's developed. right? I'm seeing 20 to 30 pages, pretty typical. People who are reporting how long they're spending on this, 10 hours, at least 5 hours. These are not, homework questions. You just sort of like scratch down the answers and turn it in. If you really want to go through the whole procedure and really get the benefit out of it, right? It takes time. Labs are a big component of these kinds of courses. It's time well spent, right? It really, really helps you to nail down your understanding of sum of products when the result of your analysis is something that you're going to have to build and test and hope works correctly, right? It's a very different experience from I'm just going to find the ones and write down these numbers over here, and I think that'll be right. It's kind of forces you to really, really think about why that gets you the right answer, right? Why is it that if I take these two things and run them through inverters, and I take those and put them through an AND gate and so on, why does that give me a reset pulse? It feels to me, and to a lot of people at least, more meaningful when it's actually like translating into something, sort of physical. It's still a simulation, but more physical. Um, so labs take time for sure, but I think it pays off later. All right, let's do a 5 minute break, and then we'll come back and we'll talk about Lab 6, and then we can move on to new stuff. So let's come back at let's come back at 9:23. All right, I'll see you back here in a few. Alright, we're back. So any final questions on Lab 5? Alright, well Lab 6 is your last lab that involves Tinkercad, I believe. Lab 7 is going to be different. It's going to use a different set of software to work with a language called Verilog. So Lab 6 is also your last traffic light control experiment, where you're going to actually, be putting this together in Tinkercad and such. We may touch on the traffic light in Lab 7, but this is sort of the grand finale of what has been a series of increasingly complex circuits related to your traffic light control circuit. So there's two pieces to Lab 6. The first is a building block for Experiment 2. Experiment 1 is a delay circuit. And then Experiment 2 is going to use the delay circuit to build a traffic light controller where you have 3 lights on each lane, red, green, and yellow. And, with the expected behavior, when you move from a green light to a red light, you go through this intermediate yellow stage where your light is yellow for a few seconds before going red. So that, if a car is halfway through an intersection, the other lane doesn't suddenly turn green on them. So this will be a more realistic traffic light. But the building block for it is this delay circuit. And so this is Experiment 1. And the delay circuit is built using the 555 and using a set of JK flip-flops. And let me show you the intended behavior of this. So here's a system diagram. There's an input, and there's an output. And the intended behavior is the following. This. And the goal is that, your output follows your input, but with a delay of 2 to 4 seconds. And that's a weird little circuit, right? If we just wanted the output to match the input, we would just use a wire. But we're trying to build something like a slow wire here, a wire that takes a few seconds to pass the input to the output. And if I raise my input and I keep it high, my output will eventually raise and stay high. It'll be a perfect copy of the input, but pushed off a little bit in time. And mostly we're going to use it to take a pulse that's coming into the input and reproduce that pulse 2 to 4 seconds into the future. So it's a slow wire. All right, well, how do we do this? So we're going to use a 7474. Which is, I believe, a dual JK flip-flop. So let's look at the data sheet for that. Sorry, it's just a D flip-flop. Oh, we're really using the 74? Okay. All right. So I think we've looked at this chip before, actually. So these are D flip-flops. They're positive edge triggered. So here's the clock going into this first one. It's just a edge triggered device. It's got an output Q, and it's got, coming from here, and it's got an inverted output Q bar. And then it has these preset and clear signals. And the preset and clear signals are active low. And on the function table, you can see anytime that clear is asserted low, the output goes low. If clear is high and preset is low, the output goes high. So to make this thing work like a flip-flop, we want preset and clear to both be high. So you're going to tie those to logic 1. And you're going to do that on both of these flip-flops. You're going to end up needing 6 flip-flops in the end. 6 flip-flops. So preset and clear will get tied high on all of these devices. Ground on pin 7, power on 14 as usual. And then basically, when the clock ticks from 0 to 1, the input gets loaded into this flip-flop. Alright, so we're going to build a circuit called a shift register. And a shift register is basically a way to take an input like this and generate an output like this. Right, to basically take some input stream and shift it in time. In programming, if you've programmed in C or some other language and you have a shift operator, if you have a number like 0 on 1 0 1 1 0 1 and you say shift left, well, it moves each of these bits over one spot. Right, so I didn't line these up very well, but this bit moves over to here, this bit moves over to here, this bit moves over to here, and so on. And so the circuit we're building is basically a shift register, and the effect is it's going to give us this delayed copy from input to output. So imagine this circuit. Alright, pair of flip-flops, D flip-flops, clocks are connected together as usual. And we're trying to build this thing. So our input is going into this first flip-flop's D input. The output of that goes into the D input of the second flip-flop, and that second flip-flop's Q output, that's the output from our experiment 1 circuit. And for experiment 1, you're going to use a 555 to generate a 2-second clock pulse. That's the same circuit you've been using in Lab 5 for experiments 1 and 2. So the same microfarad capacitor, mega ohm resistors for R1 and R2, and that will give you this 2-second pulse, high for about 1.4, low for about 0.7. Alright, so how can we use that? Well, our clock is going to come from the 555, so that's just going to be a repeating pulse train. Alright, so what does this look like? Clock. Input. And let's see what this circuit does. Let's analyze it. And so I'm going to draw an intermediate circuit. I'm going to call this Q0. That's the output of my first flip-flop. So what is Q0 going to do? So think about D flip-flops. And let's suppose, Q0 begins low. And And when we clock this first flip-flop, right, because this clock's feeding into this clock on the first flip-flop, what does the flip-flop do? It looks at the value going into its D input, well, that's what we're calling in, and it says, hey, D is a 0, I'm going to set my output to 0. And so at that point, our output stays low. And then the next time the clock ticks, which is right here, it looks at the D input, which is a 0, and so the output stays low. The next time the clock ticks, it looks at the input, and the input is a 1. And so at this point, Q0 goes high. The next time the clock ticks, it looks at the input, it's a 0, so D0 goes low. So that's what Q0 looks like. It's a slightly delayed version of the input. But it's not a good enough delay for us. The delay is happening because our input doesn't get copied to the output until the next clock tick. But you know, if this input changed right before a clock tick, this delay would be really small. But let's take a look at what the output of the entire circuit looks like. So this flip-flop, on the rising edge of the clock, takes whatever Q0 is and loads that into its output. So let's suppose this starts off low, and nothing's going to happen until its input is high. But once its input is high, at the next rising edge of the clock, that's when the input will get copied to the output. And then on the next rising edge, that's when the output will drop. So our input pulse started right here, and our output pulse started right here. And what was the total delay? Well, this is 2 seconds. This is 2 seconds. So it was almost 4 seconds. And again, this first delay is based on when you change your input relative to the clock. And that could be anywhere from 0 to 2 seconds. But once this first output goes high, you have to wait an entire clock cycle before the clock ticks again and this input goes to the output. Right at the moment that Q0 goes high, our clock has just occurred. And that high input on Q0 is not going to change this output until the following clock cycle. So our output won't go high until 2 seconds after this input goes high. And this output goes high 0 to 2 seconds after this input. So your total delay is going to be 2 to 4 seconds. So this is a circuit you want for experiment 1. And it's a simple delay circuit, but it's also a shift register. If I put in a train of 1s and 0s on the input, I'll see that same train coming out, shifted in time. Well, that's all a delay is, it's a shift in time. So experiment 1, you've seen the circuit, right? Design and implement a 2 to 4 second delay using dual D flip-flops and a 555. So wire your 555 like you did in experiment 1 and 2 from the last lab, right? Connect the output of the 555 to the clocks of the 2 D flip-flops. Input goes to here, output goes to there, final output, that's your circuit output. Alright, so what do you want here? You want to talk about what you're doing in here, right? All of this discussion that we just did. Figure that out for yourself. Put that in your own words. Describe, how the circuit is going to behave, how this implementation is going to get you there. Timing diagrams, right? So something like this. And you could do multiple versions of this depending on how detailed you want to be. You could do a version where the input changes right after the clock tick. You could do a version where the input changes right before the clock tick. You could do a version where the input changes halfway between one clock tick and another. and see how it affects this delay. And you'll see it goes from 2 seconds to 3 seconds to 4 seconds. So definitely timing diagram, system diagram. A complete schematic, part numbers, pin numbers, component values, all of that stuff. And then how are you going to test this circuit? How are you going to know if this is working correctly? And it's a really fun circuit to test. So one thing you can do is you can take your input, hook a push button up to it, pull your input up to 5 volts through a resistor, use a push button to ground it out, take your output through it, put it through a 1K resistor, put it through an LED, run it to ground. Start your simulation. And you should see the following. If you push the button and you hold it down, 2 to 4 seconds later the LED turns on. You get this very, very obvious visible delay between pushing the button. Well, so pushing the button will actually make the light turn off, because, you know, when the button's open, it's a logic 1. So push the button and 2 to 4 seconds later the light goes off. And then release the button and 2 to 4 seconds later the light turns on. Right? When you get this right, it's really, really obvious from running that simple experiment. If you just hook this up to you know, some piece of circuitry, it's not as clear. But just put a push button on there. And it's super satisfying, right? I mean, it's an absolutely unmistakable delay, right? Push the button and hold it, and a few seconds later, light goes off. Release the button, nothing happens, nothing happens, nothing happens. 3 seconds later, boom, the light turns on, right? You know you've got a good delay circuit. All right, so that's experiment 1. So, you know, also put in your observations. What did you do? How did you test this? What did you expect it to do? What happened when you did it? What do you conclude from that? Right? This is the building block for like the grand finale of all of your traffic circuit stuff. So don't sell it short, even though, you know, it's experiment 1 and it's only like 2 sentences, right? It's a real powerhouse of a circuit. And make sure you understand the circuit and how it works. And then we're going to go on to experiment 2. And experiment 2 is the full traffic light. So, three-way intersection, the usual setup, right? West, south, east, priority on the east, so on and so forth. Each direction has 1 lane, but each lane has 3 lights now, red, green, and yellow. And you should have 1 green light at a time at the most, but you may have a yellow light. Light should go from green to red through a yellow phase, and so on and so forth. You should not have a yellow light and a green light at the same time, for example. So sketch the intersection as usual. Draw a system diagram, which will now be 3 inputs for 3 car sensors and 9 outputs for 9 lights. And then document the design with whatever you think is appropriate. Could be truth tables, could be K-maps, state diagrams, timing diagrams, whatever you think works. And then implement the design to go through this yellow light transition. And for this one, you need to demonstrate the final behavior to me. So we can do this during lab hours. If lab hours absolutely do not work for you, come to office hours, right? And this is a hard thing to take screenshots of to show that it works. So demonstrate the final circuit to your instructor. That's me. And so hints, there's multiple design options. One option is to use the logic from the 3-way intersection from the earlier lab and combine that with the delay circuit. And that's really the way you want to do this. We're going to talk about, for the next week and a half, a very systematic approach to designing state machines. We're going to finish up analyzing them on Wednesday. Then we'll talk about how to design a state machine to do something. That's not the way to go about this for this lab. Right? That leads to a very, very complex circuit that nobody wants to actually implement. We're gonna use kind of a cheat. And the cheat is sort of based on this idea that, what we want is we want a light to be green, the other lights are off. And when the green light turns off, yellow should turn on for, guess what, 2 to 4 seconds, right? And then when yellow turns off, we should go red. But this is a sequential circuit. This is based on not just the current inputs, but the past state of the system. So we can't just say, hey, if there's a car to the east, let's turn on the yellow light, right? We've got to say if there's a car to the east and the yellow light is currently red, then find which light is green and change that from green to yellow and wait for a few seconds and then change it to red and now turn the east light to green. And so that's potentially complex. But there's a trick we can use. And so let me introduce this to you today, and you can think about it and start working with it. I think I gave you 2 weeks for this lab. So you've got some time not to ignore the lab, but to start working on it and then, formulate some questions and ask those. Let's go back to our old circuit. And let's just look at one lane at a time. And the circuit we build for one lane is going to be exactly the same as the circuit we build for all the other lanes. All right, so this is a big time-saving trick. We're only going to build a circuit for one lane initially. And we're going to use one of the signals from the old circuit. So let's just suppose, I don't know, we're looking at east or something. We're going to use the old green signal that we generated. So, we made a truth table with car sensors, and we gave priority to one lane, and we wrote equations and minimized them with K-maps and so on. And ultimately, the output of your earlier lab was, you had 3 car sensors coming in, and you could generate a green signal to each of the 3 lanes. All right, so here's what we're going to do. We're going to take our old green signal, and we're going to put it into our delay. And this is going to be delayed old green. So I'm going to call this OG for old green. I'm going to call this dog for delayed old green. And I'm going to make a truth table. And we've only got 5 minutes, so let me describe this to you. And you can think about it, and we can talk about it Wednesday. But there's 4 possibilities, right? So suppose the old green signal is a 0. And suppose the delayed old green signal is also a 0. So if the circuit from your old lab has a 0 going out to the green light, right, that car does not have permission to go right now. And if the delayed version of that, if that signal 2 seconds ago was also a 0, the car did not have permission to go 2 seconds ago. Okay, so abstract question. If I'm sitting at a traffic light, I do not have permission to go right now. I did not have permission 2 seconds ago. What color should my light be? Should it be red, green, or yellow? It should be red, exactly. No permission now, did not have permission a few seconds ago. I'm sitting at a red light. Alright, if I do not have permission to go, but I had permission a few seconds ago, what color should my light be? Right, that's a yellow light. This is saying, hey, 2 to 4 seconds ago, my light was green. I had permission, but right now I don't have permission. Somebody else has higher priority. My light is changing from green to red, so my light should be yellow. If I have permission to go, but 2 seconds ago I did not, what color should my light be? I've got permission right now, but 2 seconds ago I did not. So maybe I have permission because I just got to the intersection and I'm high priority. Or maybe I have permission because a car with higher priority just left. But for whatever reason, the circuitry from our old lab is saying, hey, you're good to go right now. But I didn't have permission just a few seconds ago. So I probably don't want to go green yet. Right? Theoretically, I've got permission, I should be able to go. But we want to wait a few seconds so that, whoever had priority before is slowly losing that priority through a yellow light. And so in this case, I'm going to stay red. And that's the real oddball one, right? That's basically saying, hey, I'm gaining permission, somebody else is losing permission. So yeah, while they're losing permission sitting at a yellow light, I'm going to stay red. But then after, I've already had permission for a few seconds and I still have permission, that's when I'm good to go. That's when I'm going to be green. So here is the behavior for our Lab 6 traffic lights, right? Take the old signal from your previous lab, I think it was Lab 3, where just look at the green light that you generated. Again, just looking at one lane, right? So one lane at a time. Just look at the green signal for, say the eastern lane. Take the original and also run it through the delay circuit. Come out of your experiment 1 circuit. And based on the values of those two, we can say what color should our light be. And now, you can turn this into a proper truth table by saying here's green, yellow, and red. So this should be red, this should be yellow, this should be red, and this should be green. And now you've got 2 inputs and 3 outputs. And you can make equations for this. Well, this is just an AND gate, this is a weird OR gate, and this looks like just the opposite of the delayed green. So the circuitry for this isn't bad. And you take this and you build it up, and that gives you your whole control system for 1 lane. Do that 2 more times, and you're done. Right? So this part, you've really got to be careful. This is a lot of work if you get it right the first time. If you mix something up in here, right, you'd like to be able to do something other than just rip out all the wires and start over again. So having a design that makes sense to you and that you built up and work that you can go back to and say, oh, okay, this should have been a such and such, and then you can go through and methodically change your schematic, change the wires, renumber the pins and so on, and then go into Tinkercad and change the implementation accordingly, right? That's gonna help you. So same thing on experiment 2, right? Timing diagram, block diagram, system diagram. Discussion, test plan, theory, all of that stuff, right? Alright, so think about this, ask questions next time, or, office or lab. But that should get you going. Certainly with experiment one, and experiment one is kind of its own thing. And once you've got that done, you can go ahead to working on getting one lane going for experiment two. And how are you going to test this? Again, you could just have a switch which says, "Hey, do I have permission to go for this lane?" And if you make this a 1, your light should be green. And when you change it to a 0, this light should go yellow, and then it should go red. And then when you change this input back to a 1, instead of immediately going green, it should hang out for a few seconds and then turn green. And once you've got this, all spec'd out, designed, implemented, and tested, and this is working, then you just make 2 more copies of it for your other lanes, and then you can do your full final tests where you have 3 lanes, 3 lights on each one, and you can play around with that, figure out how to demonstrate it, and then come by office or lab and show it to me, and you're good to go. And then you're done with traffic lights mostly. You're never fully done. All right, we're a few minutes over, so I'll cut it off there, but hopefully that helps. Come by office hours tomorrow if you have any questions. Otherwise, I will see you on Wednesday. Have a great rest of the day and a great day tomorrow.